now with my third lecture of this kind of series where I started with basic quantum manipulation scheme for trapped ions. And just to summarize, I think what I tried to explain is really kind of the basic tools, the basic mechanisms we actually use or reproduce nowadays on a basis in the lab to kind of manipulate and detect the state, emotional state, internal state of these ions. And also how can, this is the same control techniques applied now to many ions can actually be eventually useful to do quantum computing and simulation methods. Okay? And kind of the basic idea I outlined particularly in the first lecture is kind of how can I take the trapped ion, cool it to the ground state, so prepare a pure state of motion, and maybe eventually put it in a position state, triggering that state. Now this, of course, it's done for a single ion, it's atom, so we believe the quantum mechanics works, everything is fine. So now the question that people have started to ask, probably now the last decade, is can we actually do the same thing now with a bigger object? Okay? Maybe a large molecule, or eventually something like a nanomechanical oscillator, with 10 to 10 to 12 atoms inside there, so which is really macroscopic. So then I think the first question you have to ask yourself, why should this be interesting, or why should we go there? I think there are different motivations, and Oriol, especially Oriol and also Andrew pointed out. Going from something like atoms, people have started to go to large and large objects, for example, looking at large molecules, like the school of AMO in Vienna, and they're getting out something almost 1,000 atoms. But making this jump from atoms to now these nanomechanical systems, would be a real jump in this quantum physics of macroscopic objects. And with this, this is actually a road to kind of push this quantum classical boundary into large and large object. Simply from a academic perspective, how far can we push it, and will we find something new? So this is kind of one motivation, and one of the main motivations for a lot of people in the field. But I think there's one thing that is equally important, and that is if you look back on why people actually in the first place built these resonators. And this has to do with sensing, or mainly with sensing applications. And the basic principle is you have this nanomechanical system, and you can put a mirror up there, you can charge it up, you can put a magnet there, and because it has a large mass, it's affected by gravity. So this nanomechanical system will respond very sensitively to all types of forces in nature. And a force, it's just a simple harmonic oscillator, so forces will displace this oscillator, and this displacement can then be detected by the most sensitive detection methods. Often it's optical, but also electric readout, it can be very efficient. So now what people have done over 20, 30 years is kind of optimize this structure to achieve this process, make this very efficient, and by converting these forces into something displacement and electrical signals, and at the same time doing this while adding little noise. Okay? So now, of course, the same principle will apply once we have these oscillators in the quantum regime. We can still they are macroscopic, so we can put mirrors there, we can charge them up, we can put magnets there. But at the same time, if we manage to have them in fully quantum dynamics, we can now mediate couplings between magnetic, optical, and electric forces via coherent intermediate mechanical resonators. Okay, and then I think for this type of applications, and I kind of will motivate some how we can actually use this basic principle. And in this case, it's kind of the quantum aspect is clear because we want to couple different quantum optics without losing coherence. In the macroscopic context, in this case, I don't need a definition. So macroscopic means large enough that I can put a magnet on this. Okay. So these are kind of basic motivations. And now let's look at the first step. Okay, I started with this from the ion. First of all, we want to cool the ground state. We want to have a pure state. And this has now, we have heard about this. This is now essentially done. Okay, there are several experiments more to come, which really can bring these big objects in the quantum machine. Okay, and this is, I think, really a really important step in this whole field, which hasn't been achieved over the last 2 years. So, okay, so by taking now these thermal oscillators, so this thing which is a high mixed state, bringing it down to the quantum regime and essentially preparing it in the ground state, okay, is only the first part. So you have also heard, especially with this optomechanical cooling techniques, you always have linear interaction. Okay, so what you will be able to do is to produce ground state, maybe a squeeze state, but it will be very hard to produce something like a single Fock state or a large superposition of these oscillators. So kind of this is now the main challenge. How do I get from ground state to do something? How do I achieve arbitrary control of my motional state? And then again, the question what we should also eventually ask ourselves, what do we do with it? Okay? So the basic idea, okay, now following up the last 2 lectures where we had this ion coupled to an internal state, coupled by a laser light. So the obvious idea is, of course, take my resonator, which is macroscopic, which is just like a harmonic oscillator, and couple it to a microscopic 2-level system. And by this, do the same as we do with trapped ions. Okay, the first thing is, is this at all possible? Are there potential candidates? And the thing is, if you look at the literature, there have been actually a lot of ideas on this topic. Okay, starting with kind of the early ideas to couple a Cooper pair box to a mechanical system, where you simply use the fact that the electrostatic energy here is modulated by vibrating capacitance. Briefly after, people thought about coupling flux qubits by making use of Lorentz force interactions or magnetic coupling. You can couple spin qubits by making use of magnetic field gradients, and maybe another thing which has been put forward to couple to the strain of the defect center which is embedded in this resonator. Okay? But there's a lot of type of ideas. Many people have worked on it. You might, as a reference, you can look at this. So this, what eventually will be a book chapter. It's currently an article on the archive. And kind of at least you get a brief summary of what's in the field. It's by now, I think, quite outdated, but it's still started from. Okay, so let me now explain these ideas a little bit more detail, focusing first on charge qubits. Okay, so what is a charge qubit? A lot now about transform, but let's go a few years back when people are still talking about Cooper pair boxes, charge qubits. So here it's, if you remember Steve Kernel's lecture. So what I'm considering here is just some superconducting reservoir. It's coupled to a superconducting island by a tunnel barrier. So there are Cooper pairs which can tunnel forth and back over this barrier. And if the Cooper pair is on this small island, it will have electrostatic energy. So it will cost some energy, which is essentially the charge of the Cooper pair squared over the total capacitance. And then in addition, I can have a gate charge, so I can bias this whole thing. So if I now change the voltage on these ions, first the energy of this Cooper pair will increase, but then at a certain point it will be energetically more favorable that the next Cooper pair comes in, the energy goes down again, and so on. And if there's no tunnel barrier, this would just be this electrostatic parabolas, and because Cooper pairs can tunnel forth and back between the lead and this island, there's now a splitting, and this splitting is given here by the chosen energy. Just as a remark, by putting additional flux through this device and this loop configuration, I can change this effective splitting as well as this electrostatic splitting over here. Okay. And then what you do, so you realize that all these energies are large, they're several tens of gigahertz, so you can at low temperature restrict yourself to 2 levels of this whole diagram, and then you get what's called a charge qubit, so something which has an energy offset here, which is given by this residual charging energy, and there's a mixing over here, which is given by this chosen energy. Both of these parameters you can, in principle, tune. That's kind of the basic idea, or kind of the first idea of the superconducting qubit. So now, if I take the same things again, there's a big lead, there's a small island, so the same physics as before. But now this island, the gauge capacitance for these islands is modulated by my resonator. Okay, very simple. You have now your capacitance. So this part of the total capacitance is modulated. So you expand your capacitance, you expand your charging energies. first order a disposition operator, and you end up going like this. Okay? Again, these are the two terms of my qubit. So this is what I use to control the qubit. I have a mechanical system. For these resonators, think about a few tens of megahertz, 100 megahertz maybe. And then there's this linear coupling because, because the motion here is so small, essentially only the linear part contributes. So, and again, so if you evaluate this coupling strength, so it's proportional to the voltage here applied, and it's 1 over the distance here of this gate. There's of course only a certain voltage you can apply over a certain distance, but if you don't push these values too far, this coupling can be very large, so up to a few megahertz. Okay? And this has been first pointed out in this paper by AMO, Menko, and So, okay, so now that the basic thing you do, so you have now this qubit and this resonator. And the first thing that these guys considered in this paper was, okay, so I have this full qubit control, but let's go to the regime where this guy is 0. Okay? So then you have something very simple. You have this just an energy offset, you have a mechanical system, and here is again the thing we had yesterday, force proportional to the qubit state. Okay? So the first basic experiment you can do with the system is really the one I described in some detail yesterday. You prepare the spin of the superposition state between plus and minus 1, maybe the oscillator very close to the ground state, so let's assume it's up here, and you let it evolve. And then, okay, so here, yesterday we had this case of a time-dependent force, so here's just a static force. So essentially the separation between these two guys will now oscillate in time, so we'll go forward and back, and this was also Oriol explained in more detail. So maybe again about the parameters, so you see the maximum displacement we here can get is always this coupling parameter over the mechanical frequency. So if you use a mechanical system in the order of a few tens or maybe 100 megahertz, this can be on the order of 1. Okay, so it doesn't get terrible large, but this will be the order of 1. But okay, so in this system it might be resolvable, and Oriol also described yesterday this nice scheme how you can actually prove it and use squeezing to really make the separation even larger or more distinct. Okay, so this is here one detail I want to point out. So what these guys and also other people analyzed in the system was, so just to make this clear, so that the sequence they considered is at the initial time you make file 2, so you start from the 0 state and you create a superposition of your qubit. Okay? And this guy will evolve, and after another time you do another file 2 superposition, which ideally would bring the superposition back to the 0 state. Okay? And then, but because now if in the immediate times you have actually created this entangled state, then you find that instead of recovering this being perfectly in the ground state, you have now you have this big entanglement between motion and internal state. So you actually get an entangled state, and if you just measure then the spin, you will have a probability of 1/2 in the ground state and 1/2 in the inside state. This is really kind of, if you look at this picture, you can really say, okay, due to the fact that I have this superposition state, I get this reduction of my coherence in the qubit. Okay? And this interpretation is perfectly fine. What is not really correct is to say, okay, if I have a reduction of my decoherence, this is a signature of superposition state. Okay? Because this loss of coherence for the spin will also occur if I give you here a very thermal state or any type of noise. Okay? So this is just, so again, this superposition will lead to this reduction, but just saying I see this reduction is not a hint for observing superposition state. Okay, so now another way, so let's look at another scheme to operate the system, or look at the system. In this case, we tune this residual difference between the charging states to 0. So then we have this type of Hamiltonian, and just for convenience, I go to rotate the qubit basis. So instead of having 0, 1, I can go to x and minus x. So the sigma x operator goes over the sigma c operator, and sigma c, sigma x, and it's just for convenience. And we end up, with something is a two-level system, only oscillator, and an x times sigma x couple. Okay, this is very reminiscent of the high-drive thing we had before. And indeed, you can also now start drawing these type of diagrams. But if you just look at this Hamiltonian, you will realize, okay, so we have here energy splitting typically in a few gigahertz, and we have mechanical frequencies in the order of a few hundred millihertz almost. So this interaction, even though it creates this sideband transition, is highly off-resonant. And the difference between the ion was, in the ion we created this type of thing by applying a laser. The laser gapped this energy difference. So, okay, in the superconducting qubits we don't have lasers, but we have microwave fields. And what you can do, for example, is, that I told you before, this coupling here depends on the gate voltage, so how much charge I put on this side of the resonator. So suppose I now drive this gate voltage, so I have something that's oscillating with a frequency only 0. I will also end up with a time-dependent, time-modulated coupling over here. Then again, if I, for example, use this tricks for the rotating frame and do some rotating wave approximations, which we extensively discussed, I can, actually, by now using this frequency, kind of get this big energy difference, but minus some mechanical frequency, I end up with mainly a red sideband term, so a James Cummings interaction, and by doing the opposite, I get this anti-James Cummings interaction. Okay, they simply by instead of using a laser field to get this energy difference, we here use microwave fields. And in principle, now I can start doing all the things I told you in the first lecture. But actually, I want to point here out something which has been now mentioned, I think, a few times, especially in German's talk, about reservoir engineering. Okay? And to just explain the basic idea, let me again look at this usual sideband cooling picture. Okay, so I apply a signal on the red sideband, which creates a population. It will excite it, the qubit decays here, and it will simply go down the ladder. If I'm keeping the sort of sideband regime, I will only have this path and don't go up. So if you look at, so in principle we know what's happening, so the state will end up in the ground state. But maybe another way to look at it is if you consider this whole master equation, we have here a Hamiltonian which does this excitation, and we have here a dissipation term, which simply lets the qubit decay. So why is this the ground state, the steady state of this master equation? Well, simply because this state, so 0 times g, is kind of a dark state of this Hamiltonian. Okay? So once I'm here, there's no way that I can be re-excited. And if I'm in another upper state here, I just decay. So from this simple argument, you see that this state, so in the end, because we have a density operator, so that this type of density operator is a steady state of this master equation, simply because 0 times g is a dark state of my Hamiltonian, which excites the system. So now you can do generalize this argument, and suppose I don't have now this just this red sideband, so this A operator here, but maybe I construct something which has some arbitrary operator over here. So what is the steady state of this system? Suppose I can now identify again the dark state now of this operator, so the motion at dark state of this operator. Okay, and I see that again this Hamiltonian acting on this type of density operator gives 0, and the Liouville operator, because it's the ground state, also gives 0. Okay, so simply, so this dark state, it can be now a distribution of all populations, it will not be excited anymore. Okay, simply due to this condition. And now the basic example, which was pointed out in a very early paper here by Stiak and Peter Zoller, is if I have now, in my scheme, I on one hand have the red sideband, and I add this blue sideband. So my excitation is now not only on the red side, but in this direction, but simultaneously on the blue side. And now I can ask, I mean, which state actually satisfies that this operator acting on the state is 0? I mean, you can familiar, but if you work it out, you actually find that the state that satisfies this condition is a squeeze state. And in principle, by making, if this is much larger than this transition, it's squeeze state very close to ground state. And if these are almost equal, it's a very strongly squeezed state. Okay, so this is kind of the basic idea from what's and in recent years, I mean, people are on classes in Peter's group, I mean, they have generalized it to many body systems and so on. But it's always about kind of engineering, so one system which makes dissipation, and an engineering operator which creates a non-trivial dark state condition.
Yeah, can you say again why that acting on side B, why is that a dark state? Why is that a dark state?
So you can add, I mean, if I give you this, so I have this operator, and I ask you, I mean, can I identify a state for which this operator acting on this state is 0?
I guess the line above that where you imply that it's a dark state, why
so if let's say, if this condition is fulfilled, okay, then my Hamiltonian acting on this density operator gives 0, okay? Because I mean, if I take this part, okay, here I have a sigma minus. Sigma minus on this side gives 0, so that's trivial. If I take this term, this can excite the atom, but F on this side here gives 0, okay? So that's why the whole thing is a dark state. And okay, so I mean, this is a very, very nice idea. So here it's been first described to squeeze, squeezing of reservoir engineering to squeeze the state of dry iron. I mean, dry iron has a lot of other ways to do the squeezing, but when we looked in kind of this one of the first ideas in this direction, actually to apply these ideas now to mechanical systems, and I think in this case it's a nice way to produce a squeeze state, because you start from this linearized simple coupling, switch on your coupling fields, and simply bump into this squeeze state. Okay? So this would be an alternative way to do all this not coherent state engineering, but now on the dissipated level. And once you have produced this squeeze state, just as an illustration, now let's do all this quantum state tomography, even state construction, and see that it actually works, even if I include now dissipation and everything else. Okay. Okay, so this was just kind of a basic example. I'm also summarizing a little bit the early ideas in this field, looking at charge qubits and coupling to resonators. So what I've mainly working on in the past years is actually coupling resonators to spin qubits. And first of all, okay, so not just any spin qubits, but especially to nitrogen vacancy centers in diamond. And I think I'm still, last talk, it's still the first one measuring B centers. So
that's true, that's shocking.
That's shocking. So you have to do something in the next conference. So just to briefly remind everybody what is the basic of this B center defect, which you probably have heard or should have heard at some stage. So okay, so if you look at diamond, it has this nice diamond structure with a lot of carbons. Or in this diamond lattice. And what eventually can happen that one of these carbon atoms replaces a nitrogen atom. And then even more, what can happen is that this nitrogen atom will eventually sit next to a vacancy. Okay, so here's just an atom missing, and here one of the carbons is substituted by nitrogen. Okay, you don't have to know too much about chemistry, but the result of this defect, or this combination of defects, is that there will be bound electrons sitting in this defect, and the basic level structure now looks like this. So there's an electronic ground state, this whole defect center, which is a spin triplet. Okay, so it has 3 spin levels, ms equals 0, plus, and plus minus 1. And this is what people now used as a spin qubit. Okay, so you can maybe take these two states, create coherence propositions, and you actually find that it really works very nicely. Okay, so you have long coherence times up to 10 milliseconds even at room temperature. So even if it's sitting all in a solid, and you have nice, you can manipulate this with ESR control techniques, so using microwave signals. Okay, so this is very convenient spin qubit. But I think this is not, many defects, many spins and solids actually have this property. Okay, so that's nothing unusual. But the really crucial feature about the center is that there is an additional nice optical property. And especially if you're in one of these states, and especially at room temperature, if you look at it, the spin will sit in any of these states. But if you're now shining a green laser pulse for a while, you actually will find that it will go up and down a few times, and eventually it will decay over this metastable state down to the 0 level. So by simply shining you a green laser, you can, starting from a very big state, you can prepare this spin equal to 0 with a very high probability. Okay? So you can initialize the state, and anything you want to do quantum, you want to initialize it. So that's one of the crucial features. And at the same time, you can use the same process to do state detection. And the thing is, again, so if you start at 0, you simply will go up and down, while starting at ±1, you will go up and down a few times, and then be stuck in this metastable state, so the signal you see is much lower. So this, again, is this type of cycling transition which people use in trapped ions. I mean, it doesn't work as well here in the solid-state systems, because it's not perfect, but it allows you to prepare, manipulate, and detect the spin state. And that's really the crucial aspect why people are working on this. And finally, what is now important for the things I've talked to you, is kind of a solid-state qubit, okay? So you don't need all these fancy ion trapping things. Once you have, you look at the ion, you identify it in the center, and if you stop the experiment 1 year later, it will still be there and has the same properties. Right? So it's very convenient. Okay, so now it's, of course, a spin. Previously I talked about this large electrostatic coupling. So now we have a spin. Okay, no electric fields. It's will only give magnetic fields. So how does the spin couple to a mechanical system? And kind of this idea kind of is inspired by this, especially by Van Ruger, optimizes these type of interactions. So suppose I have a spin qubit, placed now close to the surface in the solid. I have a magnetic nanoresonator with a magnetic tip on there, which creates a very strong magnetic field gradient. And then simply looking, okay, the epicenter, so two states of this center, okay, it will be split by the magnetic field. And if this tip now moves up and down, the field will change, so there will be an oscillating star effect, Seaman effect. So the thing we are interested in, of course, doing quantum physics so let's write down an atomic for this interaction. So this is A like A, that's just the position. Sigma C, that's the level splitting. And in front we have something that is, is the coupling strength. So this kind of corresponds really in how much does my level shift if this guy moves by 0 point motion. Yeah.
So Sigma C takes, so the down stays at 0 and the up is up.
Yes. So in this case, okay, I simply will be more precise later, but I think this is really 0, this is +1.
So how can you differentiate plus and minus? So you have a tree.
Yeah, so I mean, the thing is, it's very simple. So what you usually have is you have an additional E field which splits these two states. And then if you're interested in comparing superposition, you simply shine in a microwave which has this frequency. And this is yeah. So this would be one way. But I think this is now not specific to NV center, it can be just talking about any spin. Okay, so now so this quantity is now, of course, it depends on the 0 point motion which enters here, the quantum limit. Then of course also strongly on the P field gradient. And then now we can say 0 point motion, P field gradient means to enhance gradients, you want small dimensions. To enhance 0 point motion, you want small dimensions. So let's see what we can do, going to something which is as small as possible, but I think still on a very realistic scale. So resonator 2 micrometer dimensions, 100 nanometer wide. And the distance, which can put this NV center very close to the surface, so this distance here can actually be much smaller than 50 nanometers. And really now this small distance, which increases the speed field gradient a lot, really helps you to boost this coupling. And in the end, you find, if it's just on the paper at this stage, it's not measured, but under kind of still realistic conditions, you can actually achieve something which goes up to about 100 kilohertz. Okay? It's actually really, so surprising when you first do this estimate, because this is now, a single spin on the magnetic coupling, and this is a big microscopic object. So the question is now, of course, is this 100 kilohertz, is this a lot, or what do you compare it to? And okay, so this is a coherent coupling, so we have to compare it to the main decoherent sources. And one, of course, is spin dephasing, but people are now very good at manipulating or controlling the spin, so this can be in the order of kilohertz, or it's also much lower. And the other crucial decoherence mechanism, we have heard this now many times, is actually this not only the damping of a mechanical system, but it's always this damping times the thermal. And I think this was pointed out yesterday in quite detail. So as long as we are not very close to the ground state, this characteristic rate can always be expressed in kBt times h bar over q. And this is what you do compare of. So if I now go to maybe 100 millikelvin and have typical q values and the 5 times 6, what would be produced, this value can also be the order of a few tens of kilohertz. Okay? So this kind of shows that even if you start out with a very weak interaction with the spin, in principle with this system, you can also reach strong coupling conditions. And okay, so this is okay. First, yeah.
Could you also see here what would be the decoherence gradient due to surface effects to the country level? Would you expect to have other sources of?
There will be some. Maybe I can later where I want to put charge on it. So there will be electric field noise. I think so far. You can also think. Other spins sitting on the surface. Kind of creating a path for this resonator. I think so far this is not seen, or I don't have any good data. People, these Ruger guys, the Ruger guys, they use this also to sense a single spin. So it's, so I don't feeling anybody observe this type of interaction. And of course, eventually, you also, the key is always, to make here some resonance condition, and if there are other spins sitting around, the off resonance is also strongest stressed there. But so I think this stage, I think it's not a problem, but I cannot give you a very rigorous answer on this. Okay, so this kind of shows, okay, at least kind of we have the coupling and the interactions we want. So this should be good, possible system to do some nice physics. So, but let's look at this configuration now in more detail. And again, as pointed out, there are these three levels. So just again, this ground state structure of the NV centers. So there's plus minus one state. There's this, there's this center, even in zero field, it has this so-called zero field splitting. Okay, so these plus minus one states are separated from the zero state by about 3 gigahertz. So this is kind of now this Hamiltonian. And now we see that, okay, what this interaction does, again, it shifts in principle this state up and this state down. Okay, and now to this three-level configuration. So now you realize kind of that, so this coupling is now, we have resonator frequencies in the order of maybe a few megahertz. So this coupling is, highly off-resonant compared to my level split. And the other thing is, if I want to do this trick with the superposition, this lambda, is much smaller than the omega n, so this would really create only a very tiny superposition. Okay? And so at this stage, you're thinking, okay, how do I actually, again, the problem will be how do I actually do something useful with it. Maybe another thing which one should mention now is that, the spin here, and this was a little bit related to the question, is not sitting there alone. And even if I have a single NV center there will be always some nuclear spins around. And the nuclear spins, what do they do? They're very slow, they're very slow dynamics, but they're still some random. Okay, so they will produce a random hyperfine interactions, so they produce a random key field, which, you know, on average shifts the state by something on the typical order of a megahertz. And you see that this type of interaction, you know, it has the same form. So instead of having here, this is my resonator I want to detect, I have this nuclear field which shifts this resonator. So the question is also, can I even resolve this if I have this nuclear field around? So kind of now the kind of solution, or one solution to this problem is actually, okay, so I told you about this non-resonant interaction, so let's again apply our control fields, so microwave fields, or previously laser, so which take the role of the laser fields. And now make full use of the whole three-level structure, okay? So again, the ground state, that's plus minus 1 state. For the moment, I assume that the offset field is 0. And I apply two symmetric microwave fields tuned by that. So this is now kind of in a rotating frame. So the thing about this level structure is so you see that the ground state is coupled only to the symmetric superposition of these two states, which I call here B, like the bright state. So this state is excited. And then there's the other superposition, the minus 1 minus plus, which is simply decoupled by this Hamiltonian. Okay? So this is the basic structure. You have two states, ground and this bright superposition, which are coupled by the microwave field. And there's this other dark state which is decoupled. And now, okay, so this is simple. Now this state doesn't do anything. This is a two-level system, so you can diagonalize these three states. And what you actually end up with a kind of effective level diagram. You have a ground state, you have a total excited state, which is now a superposition of these two, and in the middle there's this dark state, which is unaffected. And now you see that the relative or the relevant energy spacings here are of course given by either by the tuning or the Rabl frequency. In general, you know, they have this expression of a kind of address state. So as soon as I drive them very hard, you have this general expression.